Hello class, this is 5.3. We will learn about logarithmic functions, or we sometimes just call them logs. Okay, so a logarithmic function is a function of this form: y equals log base a of x. Right, so a is what we call the base. Okay, and what this means is that the base a raised to y will equal x. Right, so all this is saying is that the log function is the inverse of the exponential function. So remember, we learned about inverse functions in 5.1. We learned about the exponential function in 5.2. Now this is just the inverse of the exponential function. Okay, so some quick examples. Say, I don't know, log base 3 of 9 equals what? Equals question mark. Let's solve this. Let's calculate this. Well, using the above definition, that is saying 3 raised to some unknown question mark equals 9. And when you stare at it in this form, it may be more obvious to you that the solution is 2. And that's probably just because we are more comfortable with exponential equations. If this is your first time seeing a logarithm, this may look frightening, but this may look easy. But they do mean the same thing. So log base 3 of 9 just equals the exponent of 3 that will make 3 to the question mark equal 9, right? So maybe a few more examples until you get the hang of this. So let's say y equals log 2 of 8. Well, that's equivalent to saying 2 raised to some unknown y equals 8. Well, just a little bit of thought, you can figure out that y must equal 3 because 2 raised to the 3 equals 8. Right, so the logarithm actually equals an exponent. Right, the logarithm equals the exponent needed to solve this equation. And that's because the logarithm is the inverse of an exponential function. Okay. So it's good to remember this equivalency. If you ever are tripped up with the logarithm, just rewrite it as an exponential equation. Okay, and with that, maybe try a few more examples. Let's look at x equals 5 to the y. Okay, so well, perhaps we're not quite ready for this example. Before I solve this, let me remind us that a function, when we plug in an inverse, will cancel out. If we have an inverse function and plug in the original function, everything will cancel out, right? And as we said earlier, exponential and logs are inverses, so therefore we will have the property of log a, and if we plug in its inverse function, a to the x, it will equal x. And if we have a raised to something and we plug in log a of x, that will also equal x. Right, so inverses cancel out. And we can use that trick to solve this example. So if we're looking at x to the 5y and we want to solve for y, well, you just take the log base 5 of both sides. And if if you take the log base 5 of both sides, you have this, right? So all I did was I took the log base 5 of both sides of this. Right, so just take the log of both sides. That's what we're doing here. Take the log of both sides. But now we can use the property, right? We could use this property here, right? Because we have a function and its inverse, so that will cancel out. Now we have log base 5 of x equals y. The reason the right-hand side canceled out to y was just because of the property of inverses. Okay, so now we just have y equals log 5 of x. Okay, what about the graph of this? What will the graph of a log function look like? Well, let's think about this in a more general way. As we learned in previous lessons, the exponential function, where the base is bigger than 1, the exponential function has a graph that looks like this. And it always goes through the point 0, 1. We also learned that the inverse function will always be a reflection about this green dotted line. So therefore the logarithm will look like this. Okay, that's what the log base a of x will look like. Okay, so nothing surprising. This was stuff we already learned. The exponential always goes through the point 0, 1, so therefore the inverse will go through the point 1, 0. If this is the exponential, well then the log is going to be the reflection of that, about this dotted green line. The dotted green line is when y equals x. Okay, so using that template, we can graph the function we were just looking at. Right, we were trying to graph log base 5 of x. Well, from our template, we know it will have a general shape like this. It will always go through the point 1, 0. And if we need to find another point, you could just plug in a convenient point. Say we plug in 25. Well, what is log 5 of 25? If you're not seeing what this is yet, you can convert this to exponential form. In exponential form, this would be like saying 5 raised to some unknown equals 25. And so clearly the unknown is 2, right? So 2. So this point here, 25, 2 is on the graph. And that's how we graph the exponential, or sorry, that's how we graph the log function, just from this template here. Okay. Now, this log had a base 5, but we could use any number. We typically use a number greater than 1, of course. So the most popular base, you may have guessed, is e. So from last lesson we learned that e, which is about 2.71, is a useful base. So we're going to deal with it here. We will be dealing with a log base e of x, but since we use this so much in mathematics, we give it a shorthand notation. And we even give it a name. It's called the natural log. So if you see this symbol in your homework or elsewhere, this is what it means, just that the base is e. Okay, and so, you know, we have this graph for the natural log of x. We'll go through here. Yeah, and then sort of need a calculator when you're plugging in numbers into this, except for the number 1. Notice how in the general template I said if you plug in 1 to any a function like this, it'll always equal 0. Right, so we can make the conclusion that log base a of 1 will always equal 0 for any base. Right, so like natural log of 1 will equal 0. Log base 7 of 1 equals 0. Just whenever you plug a 1 into a log, it will spit out 0. Okay, now that we're a little more comfortable with logarithms, let's learn a few properties. I actually already wrote these properties down, but let's investigate these properties a little more. So I'm going to write them down again. We have the property that log a of a to the x equals x okay. Now what if these were not the same base? So notice here they were the same base, but we could do, say, log with another base b of a to the x. What does that equal? Well, here we could bring the x down, but then we're left with log b of a. So when they're inverse functions, it's nice because it'll cancel, but if the bases are not the same, then it's not so pretty. But this still is a useful formula. It could help us solve a lot of equations. You could just take the log of both sides of an equation and you could pick whatever base you want. So I'll give you an example of using this property here. Say we want to simplify log 5 of the 7th root of, let's do a 5, I guess. Start out easy. Well, if you rewrite this, the 7th root, right, so we have the 7th root of 5. Remember, that could be written as 5 to the 1/7. 7 root 1/7 and the exponent, they mean the same thing. But when it's written like this, we could plug into the above formula, and here we do have the same base here, so luckily here everything will cancel out. And we could use the top formula to just get this is also telling us something here, that log a of a will just always equal 1. So if these numbers are the same, it cancels out. That's sort of what this formula is telling you. Okay, so we could look at a more difficult example now. Let's excuse me. Let's use different bases here. Let's look at log base 7 of the 3rd root of 4. Well, that's log base 7 of 4 to the 1/3. And then using the second property, you could move the exponent down. And we're left with this here. Okay, so this property here tells us we could pull the exponent down. So pull the exponent down. And that is the power of a logarithm. It can pull exponents down, because it is, in fact, the inverse of an exponent. Okay, so let's just do a few more examples here. Let's do natural log now, so remember this is base e. So we'll start easy and use the same base. Okay, so what this really is saying is log base e of e to the fourth. So really these e's cancel out, and you know it should equal 4. But nobody writes it like that. If you write it like that, it will look weird. This is how it's written in the language here. So they canceled out because of this top property here. At the same bases. Okay, but what if the bases were not the same? So if we have natural log of 7, I don't know, 7 cubed. Well, you could simplify this by pulling the 3 out, and you have natural log of 7. Okay. Right, if we have natural log of the fourth root of 3, well, that's like saying the natural log of 3 to the 1/4. So you could pull the 1/4 out front and you get 1/4 natural log 3. Sometimes people write parentheses, sometimes they do not. Okay, let's sort of look at a different example now. Let's look at some exponential equations and learn how to convert them into log equations. So if we look at this equation here, the cubed root of 125 equals 5. If we want to write this as a logarithm, well, we just use the definition. That's let me write the definition down again if you forgot it. So log base a of x equals y. What that means is a to the y equals x. So we can start here and move here, right? And if we do that, here we have a to the y equals x. So you do log of a x equals 1/3. So hopefully that's not too bad. Let's try going in the other direction now. Let's look at the equation x equals log with a base p, some number r squared. So let's convert this into an exponential equation. Well, we just use this equivalency here. So our base is p. So it's p to the x equals r squared. Okay. And sometimes you cannot calculate a log very easily by hand, so some of your homework examples you're given something like this, right? Like calculate this with a calculator is what the instructions say. So be comfortable doing that. You could just literally type this into like a Google search or something. It should calculate it for you. Or if you have like a Casio calculator or something, it's pretty easy to type this in. You also may encounter some trick questions like, I don't know, something like this. And this is obviously a trick question. It does not exist. Because just think of the graph here. The graph of a log function looked like this. So notice the domain of a log function, the domain is 0 to infinity. You cannot plug 0 or negative numbers into logs, because just looking at the graph, it's undefined over here. So you may see a few trick questions in the homework. Okay, and then the last thing I want to talk about is change of base formula. So say we're dealing with a logarithm and you do not like the base. Well, there's a formula to change it, and it's this formula here. Log, say the base is b, we plug in some argument m, we could write it as log a m log a b. Okay, so we could change some the base. Let me think of an example here. Say we're considering the logarithm log 3 of 80. Okay, maybe we want to change that into, I don't know, a base 10. So if we want to change that into a base 10, we could use the formula here. So by the formula, we do log base 10 now of 80 divided by log base 10 of 3. And 10 is also a common base. So I mentioned earlier that e was a common base. 10 is also a common base. And 10 is a common enough base that we use the shorthand. Oh, sorry, I meant 80, not 8. We use the shorthand for log base 10 like this. So if the base is 10, we often don't even write anything for the base. So sometimes you may see log base 10, or if we just write log and we don't write a base, we mean base 10, because base 10 is so common that we have a shorthand for it. And in fact, if you just type this into a calculator, it will calculate it like this as base 10. Most calculators have a log base 10 button and also a natural log button. Okay, cool. So you could change it like that. The bottom is a little messy. Maybe wasn't the best numbers to use. But you could change a log base by using that formula. And let's see if you let me think if there's anything else I want to mention. The only other thing I want to mention is just be comfortable with shifting a graph left, right, up, down, stretching it. So if you start with this as your basic graph, and then you say you have to graph something like that, it shifts it to the right one. So you may need to review the section from a few chapters ago where we would shift functions up, down, left, right. Just be comfortable doing that with the logarithm function as well. And then you should be fine to answer all the homework questions. Thank you all for watching.